Hi everyone, welcome to Chapter 3, Geologic Time. The geologic time scale of the Earth is really quite amazing. If you were to take the entire age of the Earth, 4.6 billion years, and compress it into 1 year, the amount of time that we would have actually been here is really only a few seconds before midnight. It's really pretty incredible. The vast majority of the history of the Earth is something that we have never experienced. Our presence on the Earth is really quite insignificant. So, what are we going to try and do in this section? We're going to try and distinguish between relative and numeric ages. We're going to go in to talk about stratigraphy and the principles of stratigraphy which let us decipher geologic time. We're going to talk about what happens when we get gaps in the geologic record, and we'll see some examples of those. And then we're going to talk about the units of geologic time. So this is the geologic time scale, things you might have heard of like epochs and eras and periods and that sort of thing. If you've seen Jurassic Park, you're familiar with part of the geologic time scale in the Jurassic component there. We're going to talk about radioactive decay, and radioactive decay is a really challenging topic, so I want you guys to pay close attention when we talk about that. We'll have a lab on radioactive decay in a little bit, and that can be a little bit of a challenge. And then we'll talk about why the oldest rocks that we have are not necessarily the same age as our planet, and how we come up with the estimates for the age of the Earth when we have no rocks from the origin. So the first thing I want to do is to talk about the two different ways that we can determine ages. And talking about the age of the Earth is a little bit of a challenge since it's so vast. So we'll talk about something that is a little bit more germane to our way of thinking, and that's the age of trees. So we can represent the age of anything in two ways, an absolute age and a relative age. The absolute age is the way we usually refer to the age of things, and that is basically the tree is 23 years old. I am 40 years old. It's an absolute number. It's an integer, or usually some actually a quantifiable amount. So in a tree, the way you would do that is you would count the rings. It can be a little bit destructive. You have to cut the tree down, but you can also bore in and take a core sample from the tree and count the rings that way. I actually did that as part of my dissertation work for a while. The other way is to come up with a relative age. Now, a relative age does not assign an actual numeric value. A relative age is to say that something is older or younger than something else based on its position. So in this case, in our example, the big tree is going to be older than the small tree. And while that may not always be true, we can make some general assumptions which allow us to say that. So in geology, we determine relative ages through stratigraphy. And stratigraphy is a big word, but stratigraphy is basically the layering that exists in rocks. So we've got different layers. If you've ever driven through a road cut, you've seen these layers. Sometimes they're folded and faulted and all cracked up and jumbled. They're not always perfectly horizontal like a layer cake, but that's what we refer to as stratigraphy. The actual layers are called strata, and stratigraphy is the study of the strata, or the study of the layers, to tell us something about the age of the Earth. So let's talk about these principles of stratigraphy. The principles of stratigraphy are these rules that allow us to say something about the age of the Earth. So the first one we're going to talk about is the principle of original horizontality. That one basically says that no matter what things look like now, they were originally laid down horizontally. So the top of the layers was flat. So through time, things have been twisted and tilted and turned and folded and faulted, but originally, when that material was laid down as sediment in most cases, it was originally horizontal. The next one is the principle of stratigraphic superposition. And this is a kind of a big word, but this basically says that the stuff on the top is younger than the stuff below it. So if you've got 3 layers, this goes back to our relative dating, if you've got 3 layers, the layer on the top is going to be younger than the layers beneath it. And that's because when material is deposited, it's always deposited from the top. Now there are some exceptions to this rule. One exception is a volcanic intrusion where you actually have molten material shot up through other layers. And the other exception is when the folding has been so extensive that the rock has actually been completely flipped over 300 or 180 degrees, and the youngest stuff is now on the bottom. And that actually can happen fairly commonly, but we'll learn to identify when that happens later in the course. The principle of lateral continuity. Sediments are deposited in continuous layers. That basically means that sediments don't just abruptly end. Sediments either continue infinitely or they taper they kind of thin out and taper. So that's an important one. And then the last one is the principle of cross-cutting relationships. And this one ties in nicely with some of what I just talked about in terms of igneous intrusions. The principle of cross-cutting relationships is basically when we would have one bed of rock cutting across another. So an igneous intrusion, you've got a nice layer of sandstone. Sometime later in the geologic time scale, a volcano develops underneath of this layer, and igneous rock is shot up through that sandstone. That's the principle of cross-cutting relationships. Strata must be older than any feature that cuts or disrupts it. So that's a lot to think about. Feel free to watch this video again, because these principles of stratigraphy are really going to be important when we start to talk about other aspects of geologic dating.